In this video, we are going to focus on Lewis structures. So far in this chapter, we have learned how to develop from a name the chemical formula for both ionic and covalent compounds. When it comes to Lewis structures, we are going to focus specifically on covalent compounds. To remind you, a chemical formula is going to be a representation of the molecule, specifically because we're focusing on covalent bonds in covalent compounds, which is going to illustrate by the use of subscripts the number of each atom that is present for the elements that are in that compound. A Lewis structure is specifically a diagram that is going to show the bonding between atoms in a molecule and the non-bonding pairs of electrons that exist in the compound. When we have a Lewis structure, any time that you have two nonmetals or more, or a metalloid and a nonmetal sharing electrons, that is designated by a line. And those shared paired electrons are what we called a covalent bond. So this line represents two electrons. Additionally, lone pairs may be written around the symbol for the element in a covalent compound. These lone pairs are going to be non-bonding pairs of electrons, and they serve to depict the completion of an octet in an atom. We can see that in the example that we have, each one of the fluorines have 1, 2, 3 lone pairs. Lewis dot structures come from the idea that these dots are going to represent specifically the valence shell electrons for an atom. To remind you what are the valence shell electrons, these are going to be the electrons that are in the outermost shell for an element. So for example, if we look at what is the number of valence electrons found in sodium, we could use it by looking at the noble gas configuration, and we can observe that there is one valence electron. And how we illustrate it is by writing a single dot next to the element symbol. All of this work was done by G.N. Lewis. He made many contributions to the field of chemistry, and even though he was nominated for the Nobel Prize about 35 times, he never won. But all of his work for Lewis structures, it is still to date how we look at, in this case, covalent compounds in molecules. Let's first practice how to look at Lewis structures by looking at the abbreviated electron configurations. In other words, looking at the noble gas configurations for atoms. I'm only going to do a couple of examples here. Specifically, I'm going to specifically do B and C. Let's start with potassium. If I look at the noble gas configuration for potassium, because potassium lives here, its noble gas configuration, and let me write in the periods. This is period 1, period 2, 3, 4, 5, 6, and 7. The abbreviated electron configuration or noble gas configuration for potassium is going to be specifically argon, in parentheses, 4s1. So that means that because potassium only has one valence electron, how I write its Lewis structure is going to be K with a single dot. Then let's do magnesium. When it comes to magnesium, the noble gas configuration for magnesium is going to be specifically neon in brackets. And then we have 3s2. So the number of valence electrons in magnesium are going to be 2 electrons. So when I write its Lewis structure, is going to be Mg with 2 dots. Another way to easily look at the number of valence electrons is looking at the group number, but remember that this just applies to representative elements. So to remind you, 1A, 2A, 3A, 4A, 6A, or 5A, 6A, 7A, and 8A are representative elements, and their group number tells you the number of valence electrons, as long as you do it from the specific nomenclature or abbreviation that it is from number and letter. So what this means is that the atoms in 1A has 1 valence electrons, in 2A, except beryllium, have 2 valence electrons. In 3A, only aluminum, gallium, and indium, they have 3 valence electrons. In 4A, they have 4 valence electrons. 5A, 5 valence electrons. 6A, 6 valence electrons. 7A, 7 valence electrons. And lastly, in 8A, everybody except helium, because helium only has 2, have 8 valence electrons. Let's now review, how do we write Lewis structures? One of the things is that there are different ways in which you can do this. I'm going to outline the one that I think is efficient every time. I'm going to go and read through the steps. Then I'm going to do practice problems so we can see these steps at work. When we're drawing Lewis structures, in step 1, we're going to determine the atoms that we have in our chemical formula. And we look at the number of atoms that we have by paying attention to the subscripts. Next, we're going to determine the total number of valence shell electrons that we have within the atoms in the molecule. In step 3, we are going to then arrange our molecule, in which in the middle of the molecule, we're going to put our least electronegative atom. We can see specifically that there is a chart in which it illustrates the electronegativity for the atoms. And remember, the least electronegative is always our central atom in Lewis structures. In the next step, we are going to do what is called the skeletal structure, in which we're going to connect all the atoms around that central atom with a single covalent bond. We're going to subtract the number of electrons used by these connections to the central atom from the total number of electrons that we determined. And we're going to use the remaining electrons to complete the octets of all the atoms. Whenever we do this, we're going to complete the octets of the outside atoms first. And there's a few rules that we need to take into consideration, because there are some atoms that have exceptions to the rules. For example, hydrogen atoms only want one pair of electrons. So once you have put them in a covalent bond, they don't need anything else. So we, for the most part, in covalent compounds, don't see hydrogen as the central atom. Other exceptions to the rule include beryllium, that even though it's a metal, it actually forms covalent bonds. And beryllium only wants 4 electrons surrounding it, meaning that typically we see beryllium with 2 covalent bonds. The other exception to the rule is boron. When it comes to boron, boron likes 6 electrons surrounding it. That means that typically boron only has 3 covalent bonds surrounding it. Lastly, if you have completed the octets of the outside atoms, but your middle atom does not have a complete octet, then we're going to move into that central atom pairs of electrons in order to complete its octet. That is what's going to give rise to double bonds or even triple bonds, depending on the molecule that we're trying to build. Let's do an example of these steps by building specifically the Lewis structure for phosphorus trichloride, which is a compound that is used commercially to prepare insecticides and flame retardants. So first, let's make the list of the atoms in this chemical formula. In PCl3, I have phosphorus and I have chlorine. I have 1 phosphorus and I have 3 chlorines. Next, I go and I look at my periodic table, specifically, what are the groups numbers for these atoms? Phosphorus lives in group 5A, while chlorine lives in group 7A. So what that means is that since phosphorus lives in group 5A, it has 5 valence electrons, and that's what is going to contribute into the structure. Chlorine, let me make it more clear. Chlorine, because it lives in group 7A, for each chlorine is going to contribute 7 valence electrons. So when we multiply the subscripts for the atoms in this chemical formula by the valence electrons that they bring in, we will find that phosphorus overall is contributing 5 electrons, while chlorine is contributing 21 electrons. To find the total, we are just going to add them. So in this molecule, we have 16 valence electrons that are going to give rise to the structure. Next, when it comes to this, I need to determine what is my central atom. And if I go back and I look at the electronegativity, I can see that phosphorus is going to be less electronegative than chlorine. So that means that phosphorus is going to be my central atom. Then I'm going to connect all the chlorines around phosphorus with a line, because those lines are going to represent the covalent bonds, and each line represents 2 electrons. In this skeletal structure that was developed, I already used, out of the 26, 2, 4, 6 electrons. So I'm going to subtract them. Minus 6 electrons. That means that there's 20 electrons that I still have to place in the molecule. According to the rules, I'm going to complete the octets of the outside atoms first. Since chlorine is sharing 2 electrons with phosphorus, it only needs 6 electrons to complete its octet. So I will write 1, 2, 3, 4, 5, 6. That means that out of the 20, I use 6 electrons. So I only have 14 left. The next chlorine needs 1, 2, 3, 4, 5, 6, because it's sharing 2 electrons with the phosphorus. Since I use 6 electrons, I'm going to subtract them. I have 8 electrons left. Last chlorine also requires 6 electrons. 1, 2, 3, 4, 5, 6. minus 6 electrons. I have 2 electrons left. And since my outside atoms have their complete octets, those 2 extra electrons are placed on phosphorus. So I use the 2 electrons left, and all the valence electrons are taken into consideration to build the structure for PCl3. Let's do one more example on how to write the the Lewis structure for a covalent compound. Now we are going to draw the Lewis structure for the covalent compound HCN. As we learned previously, I'm going to make the list of atoms in this chemical formula. I have a hydrogen, I have a carbon, I have a nitrogen. Since I don't see any subscripts, that means that I have one of each. When it comes to the group number, hydrogen is in 1A, carbon is in 4A, nitrogen is in 5A. So that means that every hydrogen is contributing 1 electron, every carbon is contributing 4 electrons, every nitrogen is contributing 5 electrons. When I multiply the digit that came from the subscript by the number of electrons, hydrogen is contributing 1 electron, carbon is contributing 4 electrons, nitrogen is contributing 5 electrons. So there's a total of 10 electrons in this system. Then looking at the periodic table and looking specifically at the electronegativity values, when I compare hydrogen to carbon to nitrogen, I see that hydrogen is the least electronegative. But additionally, I just mentioned that hydrogen is never the central atom. So then I have to move on to the other 2 atoms, either carbon or nitrogen. I notice that out of those 2, carbon is the least electronegative. So that's going to be my central atom. So I write my carbon as the central atom, and then I connect the hydrogen and the nitrogen to the carbon. I placed and connected them through 2 covalent bonds. That means that out of the 10 electrons that I have, I already used 4 electrons. So from the 10, I'm going to subtract 4 electrons. So I only have 6 electrons left. As I mentioned, hydrogen is one of those exceptions to the rules. Once you bonded with a covalent bond, it doesn't need any more dots. And since I fill the octet of the outside atoms first, I'm going to fill the octet for nitrogen. Nitrogen is sharing 2 electrons with carbon, so it needs 6 electrons in order to complete its octet. So we're going to write 1, 2, 3, 4, 5, 6 electrons around nitrogen. That means that for this compound, I already used all the electrons, all the valence electrons available for bonding. And we can see that hydrogen is happy because it has its 2 electrons that it needs in order to have what we call in chemistry, quote unquote, a duet, because for hydrogen, because the one that looks like helium, it only needs 2 electrons. Nitrogen is happy because it has 2, 4, 6, 8 electrons, so it completed its octet. But unfortunately, carbon does not have an octet, but it needs an octet. In this case, since hydrogen cannot share electrons in, then nitrogen must share electrons in to share with carbon to complete carbon's octet. Carbon currently is only having 4 electrons, so it needs 4 more. So nitrogen will give in 4 electrons. So what we do is that when we share electrons, we write them as a bond. So these are the first 2. And then it needs to share 2 more. And now, when I go around and I try to identify, does every atom have an octet? The answer is yes. So in this case, the sharing of electrons between carbon and nitrogen give rise to what we called a triple bond, which means that between a carbon atom and a nitrogen atom in HCN, there are 2, 4, 6 electrons being shared. Nitrogen has a lone pair. And lastly, hydrogen is sharing 2 electrons with carbon. We can count the electrons around carbon, and as you can see, there's 4 lines around carbon. So that means that carbon has 2, 4, 6, 8 electrons. So everybody has their complete octet.